So good morning, everyone. My name is Christophe Basso. I'm delighted to be with you this morning for a one-hour presentation about Simplis. So this seminar offers an overview on using Simplis for power supply simulations. So I want to start with a very quick disclaimer. I want to state that I have no stake in this company, of course, but rather I am an enthusiastic user who started working with Simplis many years ago, and I want to share the things that I've learned. So during this 60-minute seminar, we'll cover how Simplis can replace Spice in many situations, actually, and bring additional information that Spice just can't deliver. So the piecewise linear engine, and we will see what it means, that is used in Simplis, it provides a flashing simulation time, which will let you explore the most complex switching converters through transient and AC analysis. So Spice in let's say version 1, it was originally developed in 1973 for simulating integrated circuits. Actually, it was for IC designers. And the name simulation program with integrated circuit emphasis is just abbreviated as Spice, as you know. So Spice is a linear solver in essence. That is important. So whether you start a transient or an AC analysis, Spice will first calculate a bias point and linearize the circuit around it. It repeats this exercise point by point, and you can understand that it puts a heavy burden on the computer. So depending on the components, Spice needs more or less granularity, so it will adjust the time step permanently in relationship, usually with the rate of change of the signals. So sometimes the step prediction is going down to a very small value to gain in granularity, but it can hit a minimum value and the engine fails to solve the system of equations. And you have a classical frustrating message, time step too small. So if we take the example of a nonlinear component like a diode, you can see the characteristics on the screen. We can see that its dynamic resistance RD it changes in relationship with the operating points. So depending where you operate on the curve at low current, you approach the knee of the IV characteristics, and the dynamic resistance is quite high. On the contrary, if you increase the output current of the converter, you will slide along the line and go up in higher currents, and RD, the dynamic resistance, becomes lower. So all these changes, they must be computed by Spice cycle by cycle to linearize the nonlinear component exactly at the new operating point. And because the goal is to obtain a time continuous linear equation that can be quickly solved by the engine. On the other hand, if we take a switching converter, it involves linear networks when the switch is closed or opened. We can see that we are aggregating together R, C, and L, and they are linear elements, of course, when in regular or normal conditions. However, when toggling occurs, it means when you commutate or you switch between one state to the other one, there's a discontinuity or a singularity which is introduced, and then it forbids differentiation. You need to find about a smoothing process, which is going to link the on and off or the off to on states. And this smoothing process was introduced by Dr. Chuk in 1975 under the name state space averaging technique, or SSA. Alternatively, later in 1986, the PWM switch model was introduced by Dr. Vachevarparian, and it represents a viable, simpler and useful alternative to SSA in the sense that the PWM switch model, since we consider the L, R, and C as linear elements, there's no need to include them into the averaging process, but just concentrate the linearizing effort on the commutating or the switching cell alone, so the switch and the free-wheel diode. And then you will insert the PWM switch model as you would do with a bipolar transistor. You extract the symbol from the schematic and you replace the transistor, or here the switching cell, by its equivalent average model. So an average model lends itself well to determining the frequency response of a converter. So the model needs to match the structure of the adopted DC-DC converter. The cool thing with the PWM switch model is that equations are invariant. It means the structure doesn't change whether you simulate a buck boost, or even a forward converter. In this example, and that's always what we start with when we think about a compensation strategy, we want what we call the control to output transfer function of the buck converter. So it means if I apply a stimulus at the control input, and let me start the pointer. So the control input is this one here. So if I apply a stimulus at the control input, how will this signal propagate in the power stage, which is here, to generate a response here, which is observed at the output node. And the mathematical relationship linking the response to the stimulus is what we call the transfer function. So obtaining this transfer function via simulation or the bench with the body 100 frequency response analyzer truly represents the cornerstone of any stabilization exercise. Without it, you cannot seriously think about a compensation strategy. So it's truly what you need to start with, the control to output transfer function. In this drawing, you see DC values, which are these values here, you can see, and they are displayed over the nodes. So it's always important to verify these bias points are within the expected values, because SPICE, even if it fails or it delivers goofy results, it will give you an AC response, and it could be completely out of what is expected. So it's important that once SPICE has run the DC analysis or the DC operating point, you see that the values here are within the expected results. So we wanted to have a 5-volt output. This is what we have. The duty ratio here, 1 volt is 100%, so for 17 millivolt is about 42% duty ratio, so it's all right with a 12-volt input source. So if many switching circuits can be modeled using the PWM switch circuit, resonant converters cannot easily be modeled, and they need additional work, as we will see in a minute. So when the converter understudy is well characterized, the AC response of the power stage is very close to what the hardware prototype has delivered on the bench using the frequency response analyzer. So this is an important phase because you want to validate the model and make sure that it faithfully represents the response of the converter you have built. Because once you've confirmed or validated the model, you can go back to the computer and then start sweeping parasitics value, run Monte Carlo analysis as we will see, and you can run this analysis on the computer, which is much more comfortable and than resorting to let's say a prototype in the lab. But of course, if you do that on a model that is corrupt or doesn't correspond to reality, you lose time. So it's important to validate the model with a practical measurement. Once this is done, then you can, of course, trust your model and continue the analysis on the computer. There are some SPICE packages, and LT-SPICE, of course, is one of them. They offer a functionality to implement the frequency response analyzer using that software. By inserting an AC source, and this is this AC source here, and we no longer talk about the classical .AC analysis. This is a transient analysis here, and we do like in the lab, we insert a source in series here with the resistive divider. We don't need a transformer because it's an inherently floating source here with SPICE, and then you will inject a sinusoidal waveform inside the sense input. So considering the long simulation time in this mode, because you need several cycles of the modulating signal before actually validating the magnitude and phase measurements, the solution, in my opinion, is well suited for observing the open loop gain in the vicinity of the crossover frequency, a few kilohertz, but it would be a very more complicated and long exercise for characterizing the response of a low frequency system like a PFC, for instance, because you would need to go down to very low operating frequencies. So let's have a look now at the Simplis approach, which operates differently than SPICE does. So in AC analysis, Simplis examines the time domain response of the converter to an extremely small time domain sine wave perturbation signal, because it's always important whether it's in transient analysis or using the frequency response analyzer, that when you're going to inject a sine wave into the converter remains linear all the time. So it's important because otherwise the result you may have from the converter that is pushed into its nonlinear zone will be corrupt and do not correspond to a true response. Then Simplis uses Fourier techniques to extract the response in the frequency domain. So as such, the engine is well suited for simulating switch mode power supplies of any topologies. We were talking about resonant converters before. We did not have an average model. You can use the resonant topology here with Simplis without any problem. So you just need to reproduce the converter as it will be assembled in the lab, extract the transfer function as you would do with your frequency response analyzer and the injection transformer. So no particular difficulty here. The key word here with Simplis is to model all components as a succession of linear segments. So a simple diode, for instance, can be modeled using a 2 or 3 segment approach to faithfully follow an original nonlinear spice model. So very basically, here you have one segment. When you are below the threshold voltage, which would be something like 0.65 or 0.7 here in with a silicon diode, then you are just a small leakage current. And when you start going into, let's say, the conduction mode, or you pass the threshold, then the characteristic, the slope here of this segment is 1 over the dynamic resistance of this diode at this operating point. Of course, then you can add more segment, as many as you want, but you understand that the more segments you have, the longer the simulation time will be. But the cool thing is whether you are here or here, you're already in the linear segment, in linear characteristics, and then you don't need to run a linearization process point by point as a SPICE engine would normally do. And of course, you can, let's say, transform for exploration purposes this model into a simpler one, like you start from a few millivolts here and you got a perfect diode. So several models exist to model semiconductors, whether a simple model is enough for a basic quick simulation or a more precise component is necessary to unveil particular waveforms like determining switching losses, for instance. So usually what I do is I recommend to start with perfect elements, and you show that the concept like this one here, you see these are perfect elements, perfect switch, perfect diode. Once this has proven to be sound and operates correctly and delivers the right waveforms, then you can start increasing the complexity by replacing these models. And you know that at some point, if it doesn't work anymore, you do not have to debug a completely, let's say, chaotic circuit made with components that are too complicated, but you know exactly why it was not working anymore, and you know the step that you took before. Some components, such as capacitors, accept different level of complexity and let you include parasitics hidden behind a simple symbol. So this helps refine the model without overcomplicating the schematic diagram with extra resistance and inductances. A diode, as I said, can easily be modeled with a few lines describing its behavior. So for testing purposes, a perfect diode with a low forward drop and a finite breakdown voltage characteristic is very useful to explore new structures without losing time in identifying the right model. Piecewise linear resistors, so piecewise linear because you here describe them with a couple voltage and current. So here you see I've built a very basic Zener diode. 0 volt here in forward bias, it doesn't do anything, no current. Here I have a theoretical forward bias threshold of 100 millivolts, 1 micro, then it starts conducting, but it's not what I am interested in. It's more negative clamp here, but here I'm modeling a Zener diode, and as soon as I have minus 5 volt, it starts leaking a little bit, and when I reach here minus 0.1 volt, then I have a sharp type of avalanche mode at 5 volt. Of course, you can adjust this value to model any dynamic resistance you want, but you can see how practical it is with a few lines to define a diode. Here's something very handy as well. If you want to model a saturating inductor without resorting to the classical SPICE subcircuit, which is using the Gels Atherstone model, because it represents let's say, a comprehensive but complicated approach, and it often leads to convergence errors in simulations. Here, by using a simple piecewise linear inductor or inductance, it's easy to describe the behavior of an inductance whose value suddenly diverges when the flux linkage or the volt-seconds that you apply across the inductor during the on time, they approach the saturation value. So here you've got the magnetizing inductance, which is determined here with these two equations and 3 lines of code, which is very simple to write. And of course, this simple approach, there is no hysteresis effect, but again, it's a basic model here. When you design switching power supply, especially when supplied from the AC mates, it's important to select the bulk capacitor, of course, based on the amount of ripple you want. But then in the end, the selection is done on the amount of RMS current that is going to flow inside the capacitor. And because the downstream converter, which is here, is going to be a switch mode power supply, which is regulated. So it draws a constant power, whether you have low line or high line conditions here. So the amount of RMS current here will depend on the power you absorbed here at low line. So by having here a small Excel table using that expression here, P out, which is the constant regulated value, and the bulk value here, which is going to change depending on low line or high line, then you can mimic a constant power source and immediately obtain this type of waveform, which is given for a given, let's say, power of 90 watts here. And you see that the ripple on the bulk here is going to change or to alternate between valleys and peak. It's important that your power converter always is designed for operating down to the valley level, not thermally, because you don't stay here very long, but at least here, the feedback voltage should not hit the maximum value. Otherwise, the ripple will show up on the output, and that's something you don't want. You make sure also that the transformer does not saturate when you hit this value. And then you include a margin, because you know that with the age of the capacitor, this valley here will go down farther down. So you make sure that you have enough margin when you design your switching converter. So when power on occurs on any switching power supply, the converter needs time to reach its regulated output level. So when you power up a power supply in the lab, and before you actually run a frequency response analyzer, you have a warm-up time, like something like 10 to 15 minutes, and you wait that everything is still, so the voltage on the output is no longer moving, the current are stable and everything. So depending on initial conditions, when you start a very simple converter like you have here, the inductor current can overshoot to a large value, and then it may take time before it recovers. And see, it's even worse with the PFC, and you need a tremendous amount of time before it stabilizes. So in the closed loop system, you may see the op-amp that is going to reel up first, and then will need time to meet its steady state value again. And small signal analysis must take place when all state variables have reached their final values and the output is stable. So very often the transient startup period may hamper the total simulation time. Simplis uses a specific algorithm to precisely determine when the operating period is over and steady state operation is met with all state variables that are fully stabilized. So you're just going to ignore the long and let's say difficult to deal with startup sequence. So you're going to instruct the simulator about the switching activity via a dedicated block that we call the POP trigger, which is the symbol you can see here. POP stands for periodic operating point. And this block will route a clock, which is going to instruct the program of the switching activity that you are actually having with the switching circuit. And then the program will determine the periodic cycles and check average voltages and currents are no longer changing to declare, okay, the startup period is over now, and I can run the AC analysis. The engine will analyze the circuit state variables and determine when the difference between the current cycle and the previous one is within the convergence window, which is very precise. Usually it's down to the pico value for volts and amperes. When this point is found, the simulation engine delivers a set of roughly 5 switching cycles by default. Here, this is this example to display the operating point. And again, as with Spice, you must check these values so that they correspond to what is expected from the circuit. So here, I think I wanted to have around 5 volts. So it's basically what you have. And the current in the inductor is about 20 amp, which corresponds to the 5 volt and the 250 millivolts. So here, the bias point is correct. And then, uh, as I said, Simplis uses a specific algorithm to find the steady state waveform after a certain period of time is elapsed. In this example, I've asked to start the process after 5 switching cycles. And then the POP begins. You can see here, it's searching for, let's say, what will be the final value of the current in the inductor and the current in the capacitor. And suddenly, after 5 switching cycles, it decides that, okay, it knows exactly what will be the end value. So the average current on the capacitor is obviously 0 here, and the steady state current value has to be at this final DC average value, which is given here, and the voltage has reached its final value, which is around 5 volts. So setting initial condition, of course, to bypass soft start sequences, for instance, it helps converging faster to steady state. So Simplis progresses in its process by identifying and solving what they call topologies. So topology is a unique combination of switching states operating on a specific piecewise linear segments of each piecewise linear device and states of logic gates outputs, for instance. So Simplis indicates the number of topologies which are displayed here and how many are explored during the simulation process. It also indicates how many passes were involved to finalize the simulation and of course converge towards the steady state. So when the operating point is found, so after a few tens of seconds, it's time to run the AC analysis. So here what I've done to the very basic buck converter that I had, I've added a so-called naturally sampled pulse width modulator to the buck converter example. And it's possible to extract the small signal response of the converter, but also that of the modulator, of course. And in this example, the sawtooth amplitude is 2 volts here. So yeah, exactly this one. So it means that the insertion loss of the piece of the PWM modulator will be 6 dBs. And then I fixed the DC bias point here by imposing a DC bias to have, let's say, 1 volt over 2 volt sawtooth. It's a 50% duty ratio. So 12 here, I'm going to have something like 6 volt or so output, considering the loss of the diode here. So the response of the naturally sampled modulator is supposedly flat. However, I have included here 100 nanosecond propagation time, and it will see that in a moment. It starts introducing a phase lag, which has to be accounted for, especially if you push crossover at high frequency. It's a delay in the loop that is taken into account by the Simplis simulation. Okay, so we are ready to AC sweep the circuit now. But before that, we go through an operating point that is delivered after a few tenths of second. And as I said, roughly the output voltage is about 5.5 volt. So tooth is 2 volt. And then, okay, current in the capacitor on average is equal to 0. You can see the peaks and the valleys are rigorously equal here for 50% duty ratio. And there you go. And what is interesting is that with this operating point, of course, you can extract the design value you want, like an RMS value or an average current in a particular source or component. So the goal of any AC analysis, at least with a simple circuit like this one, or let's say prior to any design of or thinking of a compensation strategy, is to extract the control to output transfer function. And here you can see it's immediately revealed, and it takes about a few seconds once the operating point has been determined to sweep between 10 hertz and 1 mega, but usually 100K is good enough, especially if you do that on the lab. And then you have the control to output transfer function. You can check the DC gain, which of course involves the modulator gain and the insertion loss. You can complicate this formula, but this is basically confirmed by the DC gain you have at low frequency here with the 15.2 dBs. And yeah, I can also probe the PWM gain, and it's confirmed as a 6 dB insertion loss, and the phase is flat until here the propagation delay starts to actually kick in. And it's important to include this propagation delay effect, especially if you deal with power electronics that are going into standby mode, where the bias current of the comparator might degrade, for instance, or might be decreased because you want to gain on standby power. And of course, if you have lower bias current inside the comparator, then the propagation delay may suffer, and it may affect or impact the transfer function of the modulator and maybe affect the phase margin you will have in the end. So it's important to include all these little details in your modulation, and Simplis does that automatically for you. Now we operate the converter in a closed loop configuration, and this is a current mode control buck converter. So inserting the AC source as in the schematic, and the same way as you would do here with the frequency response analyzer body 100, for instance, you would actually have a small resistance here, and you would apply a stimulus across that resistance. And what you do when the converter loop is closed is you disturb or you perturb the power supply. And what the loop will do is will try to energically, or let's say, reject these perturbations so that it doesn't show up on the output. And that's the issue. You will need to vigorously inject a low frequency sine wave to make sure that it propagates through the circuit and showed up on the input, but on the output, so that it can be analyzed and extracted from the switching nodes. However, if you inject too high of an amplitude, of course, you may disturb the power supply, not destroy it, but you have to be careful. But it can saturate the circuit that you don't want. So you have to carefully adjust the amplitude of this modulating source so that you do not saturate the converter. And then, as I said, the strength with which the power supply rejects the perturbation depends on the open loop. And we know as a compensation strategy that we're going to have a high gain at low frequency to have a low DC offset on the output. So this high gain is going to absorb the perturbation. So you want to make sure you have sufficient modulation strength at low frequency, but as you approach crossover, we purposely decrease the loop gain. So if you keep the same strength that you have at low frequency, you will saturate or even sometimes destroy the power supply if you truly push it into saturation. So you need to select a frequency response analyzer to decrease the modulation amplitude as you start approaching the crossover frequency. And you know that once the crossover frequency is passed, the converters operates in AC open loop. It keeps regulating, but it doesn't, it cannot reach, the loop cannot, let's say, reject perturbations anymore because there's no gain anymore. And no gain, no feedback, no control system. Here in Simplis, what is cool is that the program will automatically control the amplitude of the source. So AC1 here, the one is truly a flag which instructs Simplis that an AC analysis is ongoing, and it will automatically adjust the source at the right value inside the software, so truly that the circuit remains linear all the time. We know that switching power supplies operating current mode control are prone to subharmonic oscillations, and you need to damp the subharmonic poles, which are shown here. And what you do that by injecting slope compensation with a certain amount of slope here, which depends on the on-time slope or the down slope of the inductor, depending on which formula or expression you're going to apply. And when you do that, you start damping the subharmonic poles that show up at alpha of the switching frequency, and that's what is shown here on the graph with a slope equal to 50% of the on slope. What I like very much with Simplis, but it's true for other piece of software like LTSpice or iSpice that I was previously using, you can have a block in which you actually gather all the design equations. And by doing that here, you can truly change the target of the, let's say, control system you want to design by extracting here the values you read from the body plot, from the control to output transfer function you have obtained, and which can be obtained, by the way, using the frequency response analyzer or analytical calculation, but here we're using Simplis. And once you have entered your target information, then the software is going to automatically calculate or determine the values of the compensation elements. So here, let's say, have a crossover frequency of 10 kilohertz with a goal of the phase margin of 60 degrees. And then you can, with these keywords here, display the values in the netlist and then see exactly what has been calculated. And that's fairly convenient. It's fairly convenient and very good to learn what are the effect of changing this target crossover frequency phase margin to see immediately what the transient response will be when you affect these numbers. So the calculated components show up in the list here, and you can see here the values that have been calculated. And once you look at the loop gain, Simplis automatically displays the crossover frequency and the phase margin. So you have here a slight difference with what we wanted to have, and it can be explained for different, let's say, trails that we can explore. But basically, the op-amp transfer function starts to be included in the picture and has to be accounted for. So knowing that it will degrade the phase margin and the crossover frequency simply because you're asking to have gain at 10 kilohertz, and not all the op-amp are able to push the gain by 20 or 30 dBs, and you may need to select in that case a different type of op-amp. So once again, it's important to you test the power supply with a very basic op-amp model, and then once you have what you expect, then you replace the very basic model with a more comprehensive model, including, if possible, the DC gain and the two low frequency and high frequency poles, and you will see how they affect your transfer function. If you want to push the exercise further, you can include different things like slew rate and this kind of thing, and check the effect of a transient step to see that, to make sure that the slew rate, for instance, is not going to affect the large signal response. It can be also very convenient to use Simplis for performing AC simulations rather than resorting to Symmetrix, which is the SPICE-based simulation engine. So the added clock synchronizes the POP algorithm and more or less cheats Simplis, because Simplis is an event-driven type of simulator. So it needs switching activity to make sure that it is properly synchronized and can run its AC algorithm. So again, here you see that everything is automated. This is a type 3 compensator. So I was asking for 1 kilohertz crossover frequency with a phase margin of 70 degrees. So it's going to calculate the amount of boost, and exactly here you can see. First, once again, you make sure the operating point of the op-amp is within the right value. And if you look at the previous slide, it's automated here. And that's often a question that I've seen on forums. People tend to just put a DC bias to the input of their filter and expect to have the right answer. But it doesn't work like that, because when you have an op-amp like this with a reference voltage of 2.5 volts here with a very high DC gain, the bias here needs to be adjusted at the microvolt level, because otherwise this guy here will rail up or down and you won't see the right AC response. So either you superimpose here a DC bias and you tweak it by hand so that this error voltage is within linear range, like 2 or 3 volt, for instance, but it's very tedious. So what I do is I automate the bias point calculation with a very basic loop like this. So during the DC analysis, this guy here is a short, and Simplis automatically adjust the bias point so that I have roughly here something like 2.5 or 3 volts. And then when the AC analysis runs, this guy here opens the loop in AC, and AC sweep is done here. And when I do the bias point check, I make sure that this voltage here is what I expect from the resistive divider. And this is what I have. I've got 12 volts, so it's okay. My regulation loop works. And I have an op-amp which is biased around 2.6 volt, which is well within its linear range. And then you can see here, I've got the expected gain 10 dBs at the wanted 1 kilohertz crossover frequency. And the boost here is the 90 degrees you have here, or the minus 275 degrees, 70 degrees. is the accumulation or of the op-amp inverting mode and the pole at the origin, which is there regardless of the compensator type you use. And then in the end, when these bumps goes up like this, the difference between the two is 130 degrees, which is the computed boost, which is the boost computed by the software to meet the phase target of, I think, the phase margin target, which was something like 60 or 70 degrees. I can complicate the analysis and explore more, let's say, complex converters. Like here, this is an ALLC, which is using charge control 4390, which is very good because, as we will see in a moment, it is actually making the transfer function of the LLC converter very well behaves and like direct frequency control. It's a charge control, so it's integrating the current observed in the primary side, and then there is of course a treatment behind that. But basically, you can see the step response, which is very good. And if we look at the AC response, no problem for Simplis, even if it's a resonance structure. You have the control to output transfer function, which is very well behaved. It looks more or less like two cascaded filters, low frequency and high frequency, but in the low frequency range, it's a first order response. You can see the phase going down to minus 90 degrees here up to fairly high crossover frequency. And then you can push crossover here to 10 kilohertz without any issue. Okay. Power factor correction, and that's where we will see that Simplis is very well suited for that. It requires many analyses with the high frequency converters, and unfortunately running over several main cycles. So we're not talking about transfer response of, let's say, 100 microseconds here, but more along main cycles that can be a few hundreds of milliseconds or even 1 second if you want to look at a startup sequence. If you do that with Spice, and here it's an example of iSpice that I was using for many years. Before 30 years ago, a simulation like this would have taken probably an entire night. Here, it uses 7 minutes, but I'm forced to reduce the time step to obtain the correct granularity in case I would like to explore switching losses or this kind of thing. It's very tedious. I can use an average model, and that's something that I've done in the past very often. In that case, you, let's say, no longer require switching events. It's all average, nonlinear large signal equations from a model. Here I'm using the PWM switch model. It's in a QR type of circuit. It's a flyback, so it could be used for lightning application, for instance. And then I have here the control law that is used for controlling the error input, which is here. And you can see you have a fairly good looking sinusoidal voltage. You can run distortion measurement and this kind of thing. And it's much faster, of course, than a cycle by cycle model. And with that circuit, I can extract the AC response and think about a compensation strategy. But you see, you have to juggle between average and switching model, and which is not very convenient. In this example, we can see a 140 watt boost converter, which is operating in critical conduction modes. You can find also in the literature boundary BCM type of power factor corrector. So the path requires here the sensing of the magnetizing state of the inductor via an auxiliary winding, which is here because we wait that the magnetization is complete before starting a new switching cycle. So the compensation is made with an OTA, operational transconductance amplifier, which is again modeled in a very simple way here. And the components value set the crossover frequency around 40 Hertz in this example at high line, because we know that this value is going to drop in low line conditions unless your power factor correction has a specific feed forward stage, which is going to compensate for the DC gain variations linked to the input voltage. And what is cool is that experiments, they show that biasing the AC-DC converter with a DC source whose value is set to the RMS of the AC input gives the expected AC response. So for a 230 volt RMS type of operating condition, I'm going to bias the circuit with the 230 volt DC input. Here, the switching frequency is all over the place. It means it's a free running system. So depending on the point on the sinusoidal waveform, the frequency is going to vary. And Simplis cannot resort to periodic operating point here because it doesn't know how to synchronize properly. Now, if you run the same converter with a fixed switching frequency, like with a CCM type or a DCM type of PFC, then you can here directly have the AC input and synchronize the POP across the AC input. And it's very cool because you can then run the AC analysis in true operating conditions. I've tested it with three-phase type of PFCs and it works very well. And it's not too long. With, let's say, a few minutes, you can have very quickly the bias point of the PFC supplied from the AC line and then obtain the AC analysis directly from a bias circuit with an AC input. You see here, that's what I'm obtaining with the DC bias. It's a fairly good, let's say, simulation time. It's very quick, and then I can obtain the small signal response here with a crossover frequency of about 42 hertz and a 70 degrees phase margin. So it's extremely fast again and very comfortable to design PFC circuit using the piecewise linear engine like Simplis. Once the converter is stabilized, of course, you can run transient simulation and have an AC source here driving the converter. You can run any type of measurements like RMS current, very important in this capacitor, or check the input current distortion. And then you see the type of transient response you can obtain. You can look at the startup sequence over a few seconds. What you can't do with SPICE, because it's going to take a tremendous amount of time here with Simplis, the startup sequence is a few minutes away. When the stabilization is done, of course, you can run a Fourier analysis and look at the distortion and make sure that the peaks here remains below the what the standard imposes. We know that adding an EMI filter in front of a converter, it may affect the overall stability, and it's very important to check that the association between the two is safe. We're not going to spend, let's say, this type of thing could be a seminar in itself. I have one that I taught at APEC in 2017, and you can take a look at it in my website. But here we just going to give a very high altitude overview of what's going on. So when you insert a front-end EMI filter before switching converter, it's important to check if stability is not at stake. The filter can degrade the control to output transfer function by potentially reducing the phase and gain margin. That's what is going to happen when you insert an EMI filter without any precaution. The output impedance of the converter may also suffer alteration, and you are going to see the transfer response that is affected. So one of the issues comes from the fact that stability analysis is usually carried over the power stage while we consider a fixed input voltage here. So when you do the AC simulation here, we say V in with a small caret, V in AC is equal to 0. But when you start, let's say, including an EMI filter, this is no longer true because the current that's going to absorb the AC current, which is modulated by the stimulus here, well, it's going to show up here on the input voltage as well, and it's going to disturb the whole operation. So you need to think about it when you include an EMI filter. So when you operate your power supply, let's say if we take a buck converter in a classical voltage mode control, the converter exhibits a positive small signal that we call also incremental resistance. Okay, so if we take a buck operated in an open loop, V out is equal to dV in. So if you keep the duty ratio constant, when the input voltage increases, so does the input current, because V out is also going to increase. Now, if you close the loop and you assume that V out no longer moves if V in changes, because this is a control system, the output power is perfectly constant and theoretically equal to the input power, okay, if we neglect the efficiency or if we consider 100% efficient system. So when the input voltage increases, now in this case, the loop is going to reduce the duty ratio and the absorbed input current is going to decrease to keep P in unchanged. Now on the opposite, when the input voltage decreases, then the input current, of course, goes up to keep the output power constant. And this behavior is that of a negative incremental resistance. So you determine its value by calculating the slope of the curve here that you can see. If you plot input current versus input voltage, you have this negative behavior here. If you determine or if you differentiate here the curve at any operating point, this is what you have. You can see this is a negative incremental input resistance. Please, it's important to note that if you take the same buck but operate it in current mode control in open loop, it's already a negative incremental resistance in open loop conditions. I'm very quick example that I like. So here you have the EMI filter, which is naturally damped by losses like magnetic losses, for instance, but also ohmic losses in the capacitor, the PCB traces, or in the resistance. If you load it with a constant power type of current source, which is exactly mimicking what your power supply will do, then you see that when you start decreasing the input voltage, you increase obviously the current here because the loop is active, and you have, let's say, oscillation because this is an LC circuit, which is not properly damped. But as you start decreasing the input voltage, you absorb more and more current. And at a certain time here, you see the poles are still in the left half plane. So the Q factor is within, let's say, is below infinity, and the damping ratio is positive. But here, at some point, the negative behavior here perfectly compensates the losses incurred to the let's say ohmic element in this filter, and you built an oscillator. It's a negative impedance type of oscillator, and the oscillations are sustained. The damping ratio is equal to 0. The Q is infinite, and the poles are exactly located on the imaginary axis. And now, and that's the issue, if you start, that's another more dangerous issue. If you start increasing the current, then suddenly the poles, they drop, they jump to the right half plane, and you start having a divergence of the oscillations. The loading of the EMI filter by the input impedance of the converter. Then if you, let's say, run a very basic model, you see that you can have what we call a minor loop, which is, let's say, shown on this drawing here. And this minor loop, well, it obeys exactly the Nyquist condition. So it means you have to stay away from a unity gain with a phase which is reversed at minus 180 degrees. It's important that you sweep always the output impedance of your converter, whether it's, let's say, using the simulated models or even on your hardware. It's not complicated, but it's not dangerous either, because this source here is equal to 0, even if you have a high power converter on the bench. And then you look here at the output impedance and show how it's going to peak. Okay. And then you sweep the input impedance of your switching converter. It's easy to be done here using Simplis, and you superimpose both magnitudes on the same curve, and you check for the overlaps. Any overlaps means that Z in over Z out, or ZTH over Z in, is equal to 1. And if it's equal to 1, then it's the condition for oscillation, and you have to look at the argument of the corresponding transfer function. And you see here, without the filter, the transient response is clean. And that's the issue here, because it's a current power supply. Even if I have a disturbance, I do not exactly see it on the output, but look here, the input is clearly here oscillating, and you have to do something. You can do something by just damping the filter using, let's say, elements as shown in the literature, or look at the article that was originally published by Dr. Middlebrook in 1976, if I remember well. You have the link in the previous slides, and determine the exact damping elements for bringing the Q, the peaking here, to a value which is far away from the input impedance. And I think we've determined something like 10 ohms here. Yeah, exactly, 10 ohms to bring the Q here. You calculate exactly the damping elements to bring the Q and have a peaking of the resistance to 10 ohms. And you see that once it's properly damped, here you still have a small glitch on the input voltage, but it's quickly damped, and it's no longer a problem for your power supply. Of course, when you, let's say, cascade converters, you have to look at the interaction between the output impedance of the front-end converter and the downstream one. It's even worse when you have a distribution rail which powers other type of converters, but it is something you need to be aware of and carefully look when you do this type of association. And then you can see here, there's no problem. The buck input impedance is flying well above here the output impedance of the boost, and there is no impact on the control to output transfer function of the buck characteristics. So let's have a look now at a little bit of Monte Carlo analysis. When you know that when you select components, especially capacitors or inductors or even resistance, some of these values, either the absolute values, but also the parasitics, when you talk about capacitors or inductors, they're going to move in relationship with, let's say, the quality of the capacitor or the inductor, the temperature at which the converter is operating, and also the life of the converter. As the converter is aging, the capacitance may drop, the ESR may go up. You have to make sure that you, first of all, you design for, let's say, long life, and along the life of the power supply, the compensation strategy is such that, well, it copes with all these variations. And how can you explore all the possible combinations of these variations? You can do that through different scenarios, like worst case analysis, but it's complicated, and sometimes it leads to an over design of the power supply. But you can run Monte Carlo analysis, and Monte Carlo analysis will actually show here, will show the sensitivity or reflect the sensitivity of your converter when you start moving one of the key elements. Okay? Like the sense resistance here, for instance, which is one of them. Obviously, everyone thinks of the ESR of the output capacitor, and it's important to assess the sensitivity of your design to the variation of these parasitics and make sure that in the end, when you power this power supply in the field, the power supply remains stable all the time. So Monte Carlo analysis is a multivariate analysis, and you're going to identify many different contributors to which you're going to assign, let's say, a distribution law, which can be either Gaussian, like we see here, or uniform, or even worst case analysis if you want to push to the max of the specs or the minimum of the specs. It's quite simple to actually affect Monte Carlo tolerances to the components. And then you select what we call a goal function. And what is cool is the goal functions are already defined in Simplis, and they just write the piece of software behind the scene to let you extract some particular value you want to observe. And of course, here in stability, I want to look at the phase margin, the gain margin, and the crossover frequency, how these are going to be affected when I start assigning values. Like you can see here, for instance, this one is a capacitor affected by a Gaussian distribution and a 5%, let's say, tolerance. The same here for the inductor. I can put more components that are going to be affected, and I'm sweeping all the values here with a pseudo-random type of selection. And you see that on this particular example, the crossover frequency, phase margin are lightly affected. Of course, I could here add other characteristics of the op-amp, like the low frequency pole, the open loop gain. If you look at the datasheet of some of the op-amp, the open loop gain in the minimum value can go fairly low, and if you push crossover and have a quite high burden on this guy here, it's important to make sure that the AC response of the op-amp is not that much affected by the open loop gain that has dropped to, between bracket, quite low value for some samples. Here, in the end, you obtain this type of graphical representation where you see that the bandwidth here is going to be affected between 3.3 kilohertz and 4.1, and the phase margin is still very comfortable, not talking about the gain margin. So you see how simple it is, right? There's no need to resort to complicated analysis. It would truly be a pity not to go through this type of exercise before releasing your power supply in the field. It's mandatory that you do this type of exercise to make sure that when your friend, the buyer, is coming on your office and in your office and says, well, I've identified a new capacitor, it's less expensive. Can you tell me that this new cap is it's exactly the same value as the previous one? Can you tell me that this new capacitor is going to be, let's say, safely included into the new bill of material? Well, if you run this type of analysis and you know the boundaries between which, the ESR boundaries between which the power supply is stable, then you can safely accept or discard the proposal of changing or replacing the capacitor. Let's have a very quick look now we are approaching the end of this seminar of how to apply that to a flyback converter. So here I'm using a circuit NCP 12510, which is a small T sub 6 PWM type of controller for AC DC notebook adapters. It's a 5 volt 12 amp power supply. So I have the front end section, the flyback converter itself, and then the isolated control loop, which is performing the regulation for the selected 12 volt level. 50% voltage ripple is selected for the bulk capacitor, allowing the valley voltage to go down to 60 volts in this example for a, let's say, an 85 volt AC voltage at the input. So you may argue this is too high, not enough. Well, it's just a matter of selecting the bulk capacitor. You can choose a higher capacitance value. In the end, again, what matters is truly the RMS current that is the critical parameter that is going to orientate or guide your choice towards a typical capacitor, and also the line dropout type of characteristic. Okay, if there is a line dropout, usually you want to keep the power supply alive, let's say half or a full sinusoidal cycle, so it will impact also the capacitor selection. In the end, what is important is to exactly know the valley voltage at which you will go down to, and supplies the simulation here is very handy for that. So you replace the load here with, in the end, the selected capacitor with the right power supply constant power load, and then you will see what will be the minimum value here, and it will be the mean DC for determining the saturation current of the transformer and sizing the maximum power of your power supply. If you fail to do that, again, as I said, you may push the feedback to the limit while you start approaching the valley here, and then you will see the ripple showing up in the output. And of course, here, when the cap is aging, this valley voltage will go down. You need to have a certain amount of margin to make sure that the power supply will operate okay along its life cycle. And as I said, very often what matters, you see, we started with 100 microfarad, but in the end, I may, for this design, adopt a 180 microfarad capacitor because I want to have a hold-up time long enough for supplying or providing the power when there is a drop in the input voltage. Okay, so you see, you start with a theoretical value, and then by going through different iterations, you converge toward the final value. And then, of course, the transformer turns ratio is the parameter to be determined for flyback converter based on the maximum peak voltage the MOSFET can accept. Always apply a derating factor. Of course, it's important. So usually we select a derating factor of between 10 and 20%. So it means in the worst case, open loop failure or short circuit at the board, then the maximum voltage seen by the transistor in this mode shall always remain, let's say, within the margin that you have allocated. So let's say 10% of 650 volt below that. So having these parameters on hand, then you can, of course, look at the possible crossover frequency, considering the right half plane zero, which is the plague in all these type of converters like the boost to buck boost. So it really fixes the maximum crossover frequency. You have to stay, okay, between 20-30% of the lowest position of the right half plane zero. And then you go through the classical process of selecting the wire gauge and this kind of thing. Then you can run Simplis and check the operating waveforms with or without adding an RCD clamping network if you want. You're not obliged to do that. It marginally affects the control to output transfer function in a voltage mode converter, but for the sake of simulation and simplicity, then you can rely to a very simple circuit for AC analysis. And then the compensation strategy here, again, the control to output transfer function. I want to have a 2 kilohertz crossover frequency with a good phase margin. These values are extracted from the body plot and then entered into the macro here. And then let's go. The power supply is going to automatically, the simulator is going to automatically compute the compensation element. Of course, do not forget to characterize the optocoupler. It's important because in many papers I've seen on the TL431, people forget about that, but it's not the case. You need to extract the pole position of the optocoupler. You can do that with a frequency response analyzer. I've shown also how to do that with a simple scope, with a simple oscilloscope. And here, this guy here is going to apply an extra parasitic capacitance between the one you will place at the feedback input. So it's important to know here in the particular case where the pull-up was probably something like 20K, perhaps, yeah, 20 kilo ohms here. So you see the parasitic capacitance is about 2 nanofarad, which is quite high. Once everything is packed into the simulation templates, then you can run the analysis at low line and high line and see the impact on the body plot. Of course, then you will run Monte Carlo analysis and this kind of thing to make sure that in worst case condition, stability is not affected. And then run the transient response to show that your component selection leads to the right transient response you expect from the output. Here, what is called with Simplis, I can run the entire converter now, directly supplied from the AC mains. I could add the front-end filter, for instance. I could insert it and look at now the whole picture during the startup sequence. I can see that I have a small overshoot on the clamp voltage, which is normal. Is it enough or is it safe? I'm not sure, depending on the limits I've set, but this is the kind of thing you want to look at. And also very important, as I said, the selection of the bulk capacitor is done on the ripple current, but this ripple is low frequency, but as well made of high frequency pulses absorbed by the downstream converters. So they're all together, they define the maximum RMS current this capacitor is going to see. So it's important to assess the whole combinations of low frequency and high frequency pulses. A very small bit of advertisement. All of these templates that I've used, let's say for my seminar here, these are all free templates. I think right now you have more than 130 that you can download from my webpage. And these templates, they can run for, let's say 80% of them on the free demo version of Simplis elements. And you can run AC analysis, transient cycle by cycle simulation, and this kind of thing. So we've seen that nowadays, state-of-the-art simulation tools, they provide a tremendous assistance during the design flow of your switching converter that let you test your circuit on the computer and verify that components fulfill their function, while of course operating within adequate safe margins. So small signal analysis is an important part of the design, and SPICE needs you to resort to an average model if you want to compensate the converter. It's not necessary with Simplis because the engine can extract the AC response from a switching circuit in a few seconds. And it works with resonant converters as well, for which there is no simple and accurate model. The simulation speed of Simplis can also be advantageously used to simulate a PFC stage, as we have seen. And what is cool is that you can run that over numerous mains periods. And otherwise, it would require hours of simulations with a classical SPICE-based engine. So thank you for listening to this presentation, and I leave the floor again to the Omicron friends. Thank you very much.